Hello, my dear friends. Welcome to the Patrick Gunnels Rumble channel. I am your host, Patrick Gunnels, joined by my guest, Troy Pasulka, who is joining us from far away in an undisclosed location. Troy, how are you today?
Good. Hawaii right now.
Hawaii?
Yeah.
Oh, that sounds awesome. How's the weather over there?
It's fine. It's fine.
So, like right now, I guess you'd be like 5 hours ahead. Oh, wait, 5 hours?
Yeah, almost noon.
Okay, gotcha. So anyway, long story short, guys, the reason Troy has joined us today here on the channel is because I did the Pat and Jeff show last week and put it out over YouTube. And well, on the Pat and Jeff show, Jeff and I talked about the final experiment, which was a demonstration by some people of some things. And I argued that it was a fake, that they faked it and that it wasn't a real event. But I also said during that exact same video that when it comes to the topic of flat Earth versus globe Earth, or just the shape of the ground upon which we're standing, I will debate anybody with no prep, and at any time, anywhere, et cetera, et cetera. And with the only caveat being that it had to remain civil. There could be no shouting of insults. And Troy was actually watching on YouTube and said, I'll talk to you about it, although I don't want to consider it a debate. We're going to make it a discussion. There's things I can bring up that I think would make for an interesting conversation. And with that in mind, I said, yeah, that sounds great to me as well. And then I looked you up, Troy. And so I want the audience to get a chance to know you a little bit. You have quite the logic background in general because of what you do for a living.
Yeah, I'm a licensed attorney, although I don't practice. I just I teach people who want to get into law school how to succeed on the LSAT, which is a test of reading comprehension and critical thinking and logic and stuff like that. And I also do, business coaching and stuff like that, where I can apply my critical thinking mindset and reading comprehension skills to help people in their lives.
Yeah, and I think when we talked, you said you're a pretty darn good tutor. So anybody who's interested in taking the LSAT, you should definitely reach out to Troy. Troy, do you have like a website that people can go or a link or anything like that?
Yeah, I'm in the middle of transitioning, but I have an app on the App Store. It's called, I think it's only on the iPhone one right now, called LSAT Angel. I have a website. I think I haven't checked on them in a while. I've been busy doing some things, but it's bestlsattutor.com and lsatangel.com. You can also find me there.
Yeah, awesome. So just to get into what you want to talk about today, the topic from the Pat and Jeff show was the final experiment, which to me, it was because I'm a flat earther, as you and I have discussed. So the final experiment was a bunch of people going down to Antarctica. The idea was they'd go down to Antarctica and demonstrate that there was a 24-hour sun during the Antarctic summer. So the heliocentric model has the Earth revolving about the sun, and the tilt of the Earth changes from one end of that ellipse to the other, such that during one summer, the northern summer, the North Pole gets 24 hours of sun, and in the southern summer, the southern pole on the globe getting a 24-hour sun in the southern summer. Pretty simple stuff from a geometric standpoint. And my immediate argument was that that's still an affirming the consequent fallacy, because even observing a 24-hour sun, having it consistent with the heliocentric model doesn't prove the heliocentric model. And I think that's probably fairly non-controversial for you as well.
Yeah, let's talk about that for a second, because this is something that I teach people every day for the LSAT. Very simple example like that I often use is, if you jump in a pool, then you'll get wet. And we can accept that is true. We can imagine some crazy scenarios where it might not be true, but let's just accept that it's true that if you jump in a pool, you get wet. That does not mean that if I look at somebody and they're wet, then I can assume that they've jumped in a pool. right? They could be wet for 1,000 other reasons. So, if I think you use the language of affirming and consequent, I don't really use logic language like that. I just say, look at it. A, even if we accept that A leads to B, or if A is true, then B is true. That doesn't mean that we have to accept that B would lead to A.
Exactly. So yeah, reversing an if-then statement is fallacious would be one way of putting it. So,
Sure. I mean, it could be that both ways are true, but one doesn't make the other one true.
exactly.
But now, okay, so we agree on that. But I have a little, I don't know what the right word is, gripe or whatever, where you bring up this fallacy, but I see it a little bit differently. You tell me if I'm missing something. I don't think they're trying to say that B proves A, that 24-hour sun is proves globe Earth, even though if there's a globe Earth, then there would be a 24-hour sun.
Mm-hmm.
I think they're trying to falsify flat Earth, saying that, which is fine logic, from a logical standpoint, that if they believe that if flat Earth, then there's no 24-hour sun, and so proving that there is a 24-hour sun would prove that there is no flat Earth.
It's a great point. Let me address that. So what Troy is saying there is that in the event that there is a 24-hour sun, that is utterly inconsistent with what they call the flat Earth model. Some people call the azimuthal equidistant model, the Gleason map, and Dave Weiss shows this model all the time, which is a sun that travels, that is a local sun, and it travels along a circuit that causes day and night, and it causes the seasons, et cetera, et cetera. And in that model, there would definitely not be a 24-hour Antarctic sun during the Antarctic summer. And that is very true. It's also important to note, though, I don't claim the azimuthal equidistant model. I don't claim any model. All I seek to do is falsify heliocentrism, falsify the heliocentric globe model, and then we can move on to try to figure out what the truth is. So your point is an extremely good one, and it's important that we note it. It's also important to note that everybody who supposedly went down to Antarctica explicitly adopts the azimuthal equidistant model, which is, for me, a strong sign of controlled opposition. Because the flat earthers I know remain logically consistent. We're not here to tell you what the world is. We simply seek to falsify that which can be falsified, and that's the most we can really do. I don't have the ability to go up to an altitude of however high I need to go to determine what the shape of the Earth is. I do have the ability to falsify things, to find contradictions in logic. So yeah, very good point. And I would never claim that they are claiming.
Let me clarify also. Okay. They've probably done the fallacy that you're talking about, but I'm just trying to steel man their argument, basically.
Sure, you bet. And you know what else? Okay, I agree with you, by the way, though. They were trying to falsify a model that Austin Whitsitt, Darren Campanella, Dave Weiss, and whatever other flat earther was there, they all do ascribe to a pretty well-defined flat earth model that I personally do not ascribe to. So what
have you falsified that, or is that why you don't?
I can't falsify it, but well, hang on, maybe I could. How could I falsify it? I haven't worked hard to.
I mean, if you believed the final experiment, which you think is like a total deception, I think, then that might falsify it, right? If it was true.
So I find the final experiment, in my opinion, has been shown to be fraudulent enough that I'm willing to disregard it. But I haven't falsified the azimuthal equidistant model because, if you really think about it, the azimuthal equidistant model is just one of a whole bunch of different models that could explain what we observe. And I don't have any evidence that we have a 360-degree ice wall holding in the waters. Now,
Okay.
there's something holding in the waters, and 360 degrees of ice at the edge of our world would do the job. But I've never observed that. So even though that model happens to be consistent with what I've been able to observe, I would definitely never claim it. There are other explanations that are just as good, such as there are many other lands than the ones we're aware of. And our world is set up so that we're really just never going to travel to those places because they go beyond a fictitious, 80th south parallel latitude. And there are definitely military boats trolling those areas, preventing people from traveling beyond them.
Although even if there was extra land, there would still the land could be holding in our waters, but there would still have to be something at the edge, unless it was like an infinite something,
Yeah, so there'd be something at the edge holding in the water, and I just think that I think that honestly, I think the azimuthal equidistant model, which I really should pull up so people in the audience can look at it, but I'll just type in. It's called the Gleason map, and it's one of the reasons why it's kind of nice is because it's also basically the logo of the United Nations. Let's see if I can make that thing big enough. This looks pretty good. So I'll just share this. This is what the 24-hour Antarctic sun would falsify. There it is. And these are the continents as we know them. If you could see my magnifying glass, there's Australia, there's China, Russia, there's Africa, the United States, Canada, Mexico, and there's South America. That's, I guess, I'm assuming New Zealand. Anyway.
Let me add also, though, I don't know if this is plausible or not, but I've seen some YouTube people describing something that you could add to this so that 24-hour sun would not be falsified. It would not falsify this, like some kind of reflection, around. Yeah, I don't know if you've looked into any of that.
I did. I looked into that, absolutely. And I just couldn't get too into it because I found that the final experiment was just so obviously failed.
Right. So you don't even think there is one. So what's the use of just looking into all that?
I just think that those guys are those dudes were up to something fraudulent, in my opinion.
Yeah.
Also, it's important to note that there have been videos that claimed to show the 24-hour Antarctic sun.
Those were also false, right?
To be frauds.
Yeah.
So, it was a very high bar to clear because every frame was gone over, and we found there were enough artifacts left over that we could discard it as a fraud. And that puts those flat earthers in a really nasty spot reputation-wise, in my humble opinion. But for everybody in the audience looking at this map, the key here is this white line at the edge of the world is what globe earthers would call Antarctica. So from any location in the known world, you just travel south and bam, you come across, you run face first into some portion of this giant wall that holds in the waters of the world. This is not necessarily the truth. And to assume that it is the truth it's just not rigorous. It's one explanation. And so I don't claim this model. And I also agree that if we say that the seasons in this model are caused by one solitary sun traveling along either the Tropic of Cancer or the Tropic of Capricorn, that a 24-hour Antarctic sun would at first glance seem to falsify this as a model. So take that for whatever it's worth.
Sure. I should say that personally, I don't believe that I have any direct experience in my life that would suggest that we live on a globe. I mean, without some kind of further thought. It just looks like it's a flat plane. I don't know, and but I did, and also when I saw some flat Earth stuff a year ago or so. I was interested at first in one of these topics that you sent me an email about, which is the the retention of the atmosphere, even though we're in a void of empty space, according to the globe model.
Yeah, yeah.
That's one of the things you messaged me about, right?
Mhm. Yeah. So you asked me about my big arguments, and yeah, for me, there are three big ones. One, we can measure the Earth and it's flat. You can measure the ground itself and it's flat. The second one is we have air to breathe, which means that our air is not immediately next to a nearly perfect vacuum, because vacuums have a way of equilibrating, and then you have no atmosphere because it's been sucked out by that vacuum. And then the third one is there's no evidence of any axial rotation, because given the dimensions that we're told that the globe is, the rate of rotation would have to be at the equator, at least something like 1,100 miles per hour. And there's no evidence of that either. So those are my big three pretty falsifiable observations that you would need to be able to make to affirm the heliocentric model. And so the big one being, we have air to breathe.
I wanted to talk about that one, the air to breathe one, if that's okay with you. I have I don't have them written down or anything, but I thought about a series of questions to ask you to explore that topic with you. Is that fine with you?
Yeah. Ask me anything you want.
Uh, Can we take a step back? I don't know how well your audience knows you personally, and I don't know you personally at all. Do you mind if I ask a couple questions that are just personal? And you could just say skip if you don't want to talk about them, just so I know like what frame of reference and expertise you have and stuff like that.
Sure, no problem.
Okay, cool. Or do you have like some kind of postgraduate or professional degrees or something like that? Are you
I have
like
a Bachelor of Arts in Mathematics.
Oh, okay. I thought I saw something online where you had like a PhD or something. I don't know.
No.
Okay, maybe not. All right. So, what's been your like day job? Do you do anything scientific or anything other than flat Earth?
No, I sold. I used to work in Silicon Valley as an independent individual contributor for a software company, with a focus on finite element analysis and fluid dynamics. So my math background just kind of made me a natural fit for selling that type of software. It was simulation,
fluid dynamics software.
yeah, fluid simulation software. So
Oh, interesting. Okay, that's kind of like the atmosphere.
what's that? Yeah, well, it's this is a fluid.
Yeah.
But after my awakening, I became a podcaster pretty quick.
Okay. When did you get into flat Earth stuff?
I became a flat earther in mid 2019.
Okay. And I think if you said you basically have like an encyclopedic knowledge of flat Earth things, is that what you said the other day to me?
Yeah. I'm pretty.
Okay. Good.
I'm well versed on the thing on flat Earth and the arguments for and against it. I as you probably heard on my Pat and Jeff podcast, I'll talk about it to anyone anytime. With the only caveat being civility, which you've demonstrated that you will definitely observe. So yeah.
Sure. Yeah, I hate when people are interrupting each other and stuff like that on YouTube videos. I can't hear anything, and so I'll never interrupt you or anything.
It's funny because when I had McToon on, my own mother, who is a pretty darn, she's a full-on Glober. She's not going to give my flat earthiness the time of day. When she saw McToon absolutely lose his mind and not let me get one word in, it was the only time she was ever suspicious of Globe Earth. So the tactic doesn't work, but it is very frustrating.
It's not super related, but do you remember when Trump said in his cabinet meeting, like, Epstein, are we still talking about that? Blah, blah, blah. Like, it was like it was so off. I think he must have known because he usually has like a good poker face, I think. I think he might have been like hinting that. I think he might have been baiting the Democrats into the Epstein release. So
he's always up to something. And one of the greatest tricks he ever did was to continue to fool people into thinking that he's just acting out of instinct or that he's just got poor impulse control. There's nothing like that going on. The dude is as well planned as can be imagined.
I imagine. I don't follow him too much, but it seems like there's a method to the madness. I don't know.
Yeah, yeah.
But anyway, yeah. So McToon was anyway, weird behavior like that, like that you showed on the final experiment video and stuff like that. It usually indicates that something's up.
Yeah.
But
yeah.
anyway,
yeah. That final experiment was. I know that you watched my Pat and Jeff show. The Vapegate stuff. He's faking the cold breath using a vape.
he only had one breath, and then he's like, "What do you think about that?"
Yeah,
Like,
wait,
what do you mean? You're still breathing, and there's no more vape.
It was really bad, and I know the audience is probably. Hopefully, you caught the Pat and Jeff show, guys. But if you didn't, you should check out that one.
That was a good episode.
It's a good episode. Yeah, yeah. I was pretty happy with that one. But anyway, so yeah, you wanted to talk about the sky and the vacuum and all that stuff.
So, just so we cover all of our bases and don't skip forward in the logic, like I'll just ask some like simple questions first, and they might be boring. I don't know. They probably just have like very simple answers, but I just want to double check that we're on the same page about some of the fundamentals.
You bet.
I don't think you're opposed to that because I watched yesterday you talking to a COVID-19 guy with an afro, and you were like trying to go very slow with him, which is good.
So long ago.
Oh, okay. Was that long? Okay?
Dude, I think that might have been. Yeah, I remember exactly what you're talking about. His name was Daniel Wilson of. It was called like Debunk the Funk. That's what.
Yeah, Debunk the Funk. Yeah.
Yeah, that was interesting time because that was back when I wasn't as solid on the virus debate. I was much when I went up against Steve Kirsch. That was when I had my P's and Q's minded more, which is a shame because that guy, Debunk the Funk, knew his stuff way better.
And he seemed pretty smart.
He knows all of the procedures, and he knows the arguments in favor of. And so, I mean, I held my own just fine, but I would have liked to have had a chance to talk to him after I had spent another year studying that topic. But that's neither here nor there. The virology stuff is my other big thing. So when it comes to globe Earth versus flat Earth, I can speak to anybody on that topic. And when it comes to viruses, the history of the discovery of viruses, germ theory in general, I feel very confident I could speak to anybody in the world on that topic as well. Those I've gone down to the very foundations of, I think, and I'm always open to be proven wrong. But yeah.
Okay, cool. So yeah. Anyway, I'm gonna go slow, like you were trying to get him to go slow, but it shouldn't take too long. So just basic like atomic theory. I'm trying to get your opinion. Like if you take a piece of gold and cut it and cut it and cut it and cut it, can you cut it forever, or at some point will it not be a piece of gold anymore? What's your opinion?
I have no way of having an opinion on that topic. I know what the scientists tell us, and that gold is an element. And I have no reason to dispute that. And I also know that models of material behavior indicate that gold stays gold as much as
until it's atomic, right?
Yeah, as well.
Basically,
if you use the term atom as
very small, very small,
defined as the smallest possible thing you can have with it still being gold, then it becomes kind of tautologously true. But at the same time, I am not a person who is going to say that I know for sure that gold is indivisible and that atoms are a real thing. What I say about chemistry is that chemistry in general is an extremely effective model for predicting the behavior of materials under a wide number of conditions. And you can use it to turn some things into other things reliably. And it is a great way to make things, to just to do technology, to create things in our world. However, because it is predictive, does not necessarily mean that,
It's true.
yeah, it does not mean that it is true. It
Yeah.
means only that it is able to, that it is useful, and that it's hard to explain this in a way that doesn't simply repeat what I'm saying. I've wanted to explain the concept of reification fallacy, because the model is not, the map is not the terrain, is the saying that you use. So I'll just put it this way: the map is not the terrain. So you got a map, and the map is faithfully drawn. You know, it's a map of your neighborhood, right? And it's got all the streets, it's got all the houses, it's got all the house numbers on it. It may even tell you what all the houses are made out of. And the map is incredibly useful, but the map is not reality. And that's what I mean when I say reification fallacy. Chemistry is a map of, it's the best map that we've probably got right now as to how materials behave. But it doesn't mean that atoms, as they are described in chemistry, actually exist.
Sure. Yeah, yeah. I mean, I was a philosophical materialist for 30 years, and it seemed totally fine to me. But
30 years?
maybe what?
30 years?
Well, I'm 30 something years old. I can't remember, but so my whole life basically.
Okay, yeah. So philosophical materialist. I
was.
And so you aren't anymore.
Yeah, no, I remember like 15-ish years ago, I heard something about the hard problem, but I never really looked into it. But then a year or two ago, I started watching some Bernardo Kastrup lectures on YouTube and conversations. I don't know if you know him, but he created the philosophical school of analytical idealism, and it's a philosophical idealist school, if you know what that is. And anyway, he was just like, yeah, the hard problem's obviously unsolvable and malformed, and you can't possibly generate experience, which we have from dead matter. So obviously, dead matter is not generating experience. And
yeah, I think.
And so fundamentally, assuming that the world is like kind of one thing, it's probably like an experience more than bowling balls and stuff.
Oh, God, yeah, I think I went through a similar journey, although I didn't formalize it like that. I do think that I spent a great majority of my life as a philosophical materialist. And it's a crazy thing when you break that. But yeah, that's where I.
Yeah. So I just bring that up to say, I'm not saying that atoms, are the end all be all or whatever. Yeah, I agree that it seems like a materialist model. It seems to work pretty well. You can pretty reliably say how much, X you're going to get if you mix this much gold and that much this. And, it seems like there's atoms because you can, So anyway, I don't even think physicists believe that atoms are real fundamentally, but the leading physicists.
That's a great question. I have spoken to a theoretical physicist with a PhD, and he thinks atoms are real. That's just one dude. So
many do. Many don't. It's quantum mechanics stuff, waves and stuff like that.
Yeah, I'm interested in what these models predict. I would love to hear that they've figured out a way to actually observe things at that level in a way that doesn't produce artifacts. For example, an electron microscope, you're already just messing with your sample so much that everything you could be looking at in an electron micrograph could be just an artifact of the preparation. And if that's the case, then what are you really looking at?
Sure. Okay. I just asked about that just to kind of establish a baseline that we could at least talk about as a model that, there are atoms or something like it. It's very small pieces of stuff. And then to go from there and say, okay, well, oxygen, nitrogen, hydrogen are also atoms. You can freeze it, liquefy it, just like, water vapor or whatever. So what we're dealing with when we're talking about the atmosphere and being sucked out is seemingly little bits of stuff, little atoms of
gas, We're talking
Yeah.
about gas, and gas
Yeah.
has very observable behavior.
Sure. Which, probably sounds obvious to anybody listening, but I just wanted to check all of our bases, make sure we're on the same page at those basic levels.
Mhm.
Okay. Transitioning for a second, why do you believe that this pencil falls when I let it go?
I think you don't have to have an explanation for everything that is a law. So I
Sure.
think I observe that as a law. That
I don't
in
think that
our-
science knows why this falls actually, but I don't know. I'm just wondering if you have any idea.
Well, I observe in our world that we live in a density gradient, that the denser things are arrayed lower to the ground, and then as things get less dense, they get higher up. For example, helium, which is extremely not dense, it'll rise above air, and the air that we breathe is of a certain density. Solid objects are all denser than air, and therefore they fall through the air down to until they hit something that stops them. That is the law of, I don't even know what to call it, really. It's just the law of the way that things are arranged in our world. And I don't know the cause of things being that way, in the same way that I don't know the cause of entropy or the cause of lots of things that are laws. I regard them as ontological primitives of our world.
You agree that a thing's mass, not separate from its density, but that a thing's mass affects the rate at which it falls?
I don't think so. No. I think that its density affects whether or not it falls or floats.
Okay, so I think you might be wrong about this, and I think I devised a way of explaining it. Let me see how it works. So if I drop 1,000-pound weight and a 5-pound weight, you agree that they hit the ground at the same time, even if I'm not in a vacuum, they'll hit the ground at the same time?
Mhm.
Okay. And if while they're dropping, I push them with my hands, I can push the 5-pound one more than the 1,000-pound one. You agree? Like pushing them laterally, horizontally.
Mhm.
So that would be basically inertia, right? The more massive one, same density, they're made out of the same thing. It's just one's bigger. Same density per square inch or whatever. So the more massive one has more inertia, right?
Sure. Yeah.
You following?
Mass times velocity.
Yeah.
That's
So, and the velocity, I guess, like in our frame of reference, would be 0 laterally, horizontally, and then until I push them, and then
they have momentum.
Yeah.
And that is force. It's a way of producing force.
Yeah. So I think that establishes pretty well that inertia exists, that like the more mass you have, regardless of your density, even if you're the same density as something else, you will stay in place to a higher degree. But when a force is applied to you, right?
Can you say that one more time?
Sure. So if I have a huge weight and a little weight made of the exact same substance, I let them drop, but I let them drop, but I push them. I'm not really going to be able to push the huge one a lot, but I'm going to be able to push the 5-pound one and displace it horizontally.
I think I can't imagine that I would have anything to disagree with about that.
Right. I don't think so. And so that establishes that even if they're the same density, if you have more mass, you're going to be harder to move.
That is true.
Yeah. So think about this then. They're the same density, but they're falling at the same speed, even though one's much harder to move. So there must be a bigger force applied to the bigger one because it still moves. So the force of the falling, or the force of gravity, or whatever you want to call it, is proportional to the mass, not the density.
That doesn't follow. The rate that it's falling is determined by its density.
But they both, they fall at the same weight. But we've already established that the heavier one is harder to move, but yet it's moving the same way.
Well, no, because you were simply talking about force as applied by us, as opposed to the simple observed motion of mass toward the ground, acting according to a law that we observe, which is a density gradient. So whether I don't claim a force, I simply
But
claim
like to fall, there must be some force being applied to it because it doesn't move.
it doesn't follow.
Or is it,
No.
okay, so do you think that, but we have established that horizontal movement would require a bigger force for those two blocks to accelerate forward.
Yeah, we have
right?
this wonderful. So we have this case where we have a observable law that things fall towards the earth according to their density, and things of similar density, they will fall through the air, which they are denser than, and they will do so at the same rate. I don't claim a force was applied to them. I simply say that we observe this is a law. The end. It is a primitive. Now, we can talk about force as a model, force equals mass times acceleration, when we're trying to apply a force to something, but we know what happens when we drop things. And it is based upon what is dense and what is less dense. And that
it correlates allegedly with that, but when you're saying based upon, you're saying that is the cause, but we don't know that, right?
I don't claim a cause for.
Okay, so it's just a correlation that you think that you see dense things falling, and like sorting themselves out or something like that, right?
Yeah, they sort themselves out. It is a gradient. I don't mean to short circuit your line of reasoning, but
you're fine. And my line of reasoning doesn't necessarily depend on this. I'm not sure, but I just wanted to start with this topic.
Okay. But I don't want to. Yeah. What I would like to say, though, I think what you're moving towards is gravity, which is consistent with the heliocentric model, with Newton's law of universal gravitation, which argues that mass attracts mass, or in the Einsteinian model, that the observed effects of gravity are the result of the bending of space-time in pseudo-Riemannian force space. But in any one of those models, in my opinion, we're just talking about a reification fallacy when it is simply observable that a law exists that arrays things according to their density vertically.
Okay. So that's fine. I'm only talking about this because if we're going to talk about the atmosphere getting sucked up or whatever, we need to talk about what holds things down and get the fundamentals clear on that, as clear as we can get. So here's my thinking right now. Sorry if this sounds like repeating a little bit, I'm not sure if it will or not, but if horizontal movement is according to mass, like according to force, which is according to mass or something like that, then it would be a little bit strange if like vertical movement was just totally a separate thing. But it could be, I guess, but it just seems like it would be the same. I don't know. What do you think about that? I think I have more thoughts, but maybe I just stop there for a second.
Well, when you drop an object and it hits the ground, it definitely exerts a force on the ground. It hits the ground, and you have the effects of force. But I'm not sure where to go from there.
Well, nowhere in particular. I'm just trying to establish, as much as can be, that the force, that probably there is some kind of force or something pulling down or pushing down from above or something, that is proportional to mass,
Okay. Well,
not necessarily
okay.
density.
So let's go ahead and steelman this. We're talking about solids, and solids have their own
Sure.
behavior.
Okay.
Liquids have another set of behaviors, and gases have another set of behaviors.
Although we've kind of established sort of that they're all made of atoms, right?
I did not establish any. No, we didn't.
Oh,
We
I thought you
established
agreed
that
that.
we
Well, at least as
established
a model, I thought you agreed that, like,
they're
you know,
made
you
of,
can
they're made of stuff.
you can turn water into, you know, gas or something.
Yeah, and that happens. We can observe that. Gas has a different behavior entirely from solids and liquids. And one thing we do know is that downward motion, that uniform downward motion that you get from solids, none of that ever applies to gases. Gases move about freely in all directions.
Well, if you have two gases in a room and one's like very dense and there's no
they get arrayed
fan or something.
They get arrayed by density. But even in their density layer, they move about freely in all directions. They're not pulled unidirectionally the way solids and liquids are. They move about freely in all directions within their density layer. And the less dense gases will array themselves higher up than the more dense gases. However, they don't get pulled down the way that solids do. And they are 100% subject to the behavior rules that apply to the behavior of gases, which are not unidirectional. They move everywhere all the time. And as a result, in my opinion, and I don't mean to, try to short circuit.
The solid's irrelevant, basically.
Yeah, talking about solids is irrelevant when it comes to trying to argue that we have an atmosphere because of gravity, which is where I see all of this going.
Maybe I don't know. That's not something I've thought about saying. I'm not sure. I'm not sure exactly where all this goes, but it seems to me that, number one, if water can vaporize and turn into still water and then recondense, I mean, it seems like they're made out of atoms the whole time. Mm-hmm. We can do that. You would agree with nitrogen, oxygen, take it from gas to liquid to solid, back and then back and forth, and so it seems like they're all made of atoms.
Okay,
whatever that is, sure, and so it seems like they're. If you're saying, well, a solid is different than a gas, well, yeah, but there's similarities too. So I don't think it's just irrelevant to talk about solids.
Okay, so
because a gas is made out of solids, right, basically, so just less dense solids.
Okay. Matter. What do you think? Let's talk about matter. So we'll speak in the terms of science, right? So we have three states of matter. We have solid, liquid, and gas. And in each one of them, they have fundamentally different behaviors. And that's why we categorize them as such. In the case of a solid, it falls to the ground. It is denser than all gases. The funny thing about solids is I think there might be a solid that is so light that it floats on certain types of gases, but that's
probably,
yeah. I've heard of something like that. Anyway, but gases are have a particular set of behaviors that, in my opinion, falsify the concept of mass attracting mass as a model for what not Newton, but what we call Newtonian gravity. Furthermore, there is no evidence of the so-called mass attracting mass theory of gravity other than a very old experiment done by a guy named Cavendish that has never been able to be reproduced. what I'm getting at is that let's say for the sake of argument that there is a force pulling stuff down. It's definitely not pulling down gases in the same way, because if it were, then we would be sweeping gas off the ground.
Well,
so there's a just real quick.
Yeah,
There's a
sorry.
fundamentally different way that gases behave. They move about freely in all directions at all times. No, it's just there's no way around that when it comes to the way gases behave. And so if they were immediately adjacent to a 10 to the minus 17 torr vacuum, as we're told is in space, then every single one of those would go to fill the available volume. And in this case, well, that available volume would be 10 to the 80th cubic meters, because that's what Neil deGrasse Tyson says our universe is the size of. All of that to say that in the model, heliocentrism, which has our atmosphere immediately next to a perfect vacuum with no containment, the gravity explanation simply doesn't work.
Okay, so if I took all the air out of this room, created a vacuum, then put a bunch of purple air in, and then I had a canister of blue air, and it was sealed, and I unsealed it near the floor, it would come out and it would be near the floor for a little while, right?
Mm-hmm.
And then I could take this bowl and I could actually sweep up the blue gas, and there would be some blue here. So you actually can sweep up gas, but we just can't see it. So it just gets a little bit confusing, I think, for that reason.
It was,
also,
okay.
Go ahead.
No, you go ahead.
Okay. Also, you said that gas, if it was being pulled down, like wouldn't act the way it does, but actually it would. If it was being pulled down, it would hit the ground, and the ground is much bigger, so the ground would not move, and then the gas would bounce back up, and we would see gas just bouncing around, which is what happens.
Mm-hmm.
So it does seem to me that just like it does seem plausible, until you explain why it's not, maybe, it does seem plausible that mass attracts mass as a model. I don't even think scientists believe that. They believe in curved space-time or whatever. But as a simplified model, mass attracts mass. Things follow solids at a rate proportional to their mass, and gases are no different. Seems like it all fits together so far. You're like, well, you can't sweep up gas, but you can. Okay. And you're like, well, gas is just bouncing around, but that's what it would do.
Well, for that to work, you're needing to just kind of ignore the fact that gases behave in a fundamentally different way.
But they don't. I just showed that you can sweep up gas and they will bounce around.
All right. It's not that you can.
I mean, like a ball bounces too. Like if you throw a ball at the ground, it bounces just like gas.
A gas, the particles of a gas move in all directions. The particles of liquids and solids move down one direction.
That's not true.
It is true.
No, they move around. Brownian motion and stuff like that.
No. We have things we can observe. Please, just stay with me. Solids move down when you drop them. Gases do not. Liquids move down when you drop them. Gases do not. They move all over the place.
So a dense gas would fall-ish, right? In a less dense gas.
A denser gas will settle and then move
in
all directions within its gradient layer, and that's observable. And
I'm not seeing the real difference in behavior, I guess. You keep saying they're totally fundamentally different. I'm just not really seeing. I'm seeing a lot of similarities. It seems like. I mean, there's some differences, especially when you get into what our human eyes can observe. But there seems to be a lot of similarities. They're made of atoms, just like the solids. They can convert it back and forth to each other. In fact, if you said like, oh, the gas is fundamentally different, but if you set liquid oxygen on fire and real oxygen, like if you set a match, they'll both explode.
We're missing the main point here, which is that there is no such thing as gas pressure without a container. The gas law says PV equals nRT. That's pressure times volume, right? And volume.
So, okay, so
requires a container.
go ahead.
So if you don't have a container, then you can't have gas pressure, because that's how gases work. Those laws don't work with solids and liquids. They have different laws that govern their behaviors. Volume in that gas law only can make any sense if there is something with volume, a container, a solid container to contain the gas. Well, what would be the container in the case of our breathable air? Well, in the heliocentric model, there is no container. That is a direct violation of the gas laws, the way gases behave. And unfortunately, at this point, I think gravity just becomes an ad hoc explanation. And it's something that we don't observe. We observe solids and liquids behaving in a way that says we live in a density buoyancy, a density gradient or a density and buoyancy gradient with some electrostatic forces involved. But the most important thing here is that PV equals nRT says there's a volume, and volume only exists if there's a container. Otherwise, there's no way to compute volume. And the heliocentric model requires that there is no container. It's just a contradiction of the gas law.
Okay. I think you're skipping ahead a few steps, but that's okay. I wanted to really build up our fundamental knowledge of what's going on at the fundamental levels so that we don't miss any logical steps as we go ahead, but it's okay. But just to clarify, obviously gas is more dense than a vacuum, right?
Yes.
And you believe that dense, yeah, right. Something is denser than nothing.
Mm-hmm.
And that could be because gas is made of atoms, so it's it's more dense than nothing because it has stuff. But whatever. You believe that dense things flow downward, right?
I observe that dense
relative to less dense things.
Mm-hmm.
So what about so then we might expect there to be a vacuum above gas.
So I think I can probably condense what you're saying. You're noting that things get less dense as we go higher and higher, and then they would.
Well, no, I'm just saying that in the globe model there is vacuum, then there's more dense air.
You're saying saying there's a density gradient because we observe things get less dense the higher you go. And
well,
then
I'm not even really talking about that. Like, forget about a gradient. Let's just imagine a simplified model where there's vacuum and then air, like no gradient. Like in that, if denser things go down, then wouldn't it just stay down?
What's the question?
You say that denser things fall down and go down. So why would we expect the gas to just go up into the less dense stuff? Wouldn't it stay below the less dense stuff with no container?
With no, no, because you can't have gas pressure without containment.
Well, forget about that for a second. You said that less dense, like more dense stuff will go down relative to less dense stuff. Like even dense gas will go down.
Yeah.
So
all of that only works if there is containment for the gas pressure.
Okay, so you're saying all of that only. Okay. So you think that all the gas behavior we see and stuff like that only works because you're assuming there's a container, or
what I'm saying is there is no such thing in any observation ever of gas pressure without containment.
But okay, so what if I have a glove that's a box
Yeah,
that's
you have a glove that's a box. Okay, go
yeah,
on.
it's like airtight here, but it's like a box around me, all around my hand.
Just your
But
hand.
that top is open, no containment there. My hand is still feeling the pressure of the gas, right?
Hang on. Yes, it's open. It's not contained. Yeah, you're feeling gas pressure.
So there is pressure without containment.
Okay. So you see what you're doing there. All right.
I know. I just want you to go ahead and tell me.
Okay. I'm assuming you're saying, okay, my hand is feeling gas pressure.
Yeah.
So there must be a container.
Well,
Even though
that's
this
what you're
container is
saying.
open. Okay. I'm saying I need to see an example of gas pressure without containment.
Why is this not an example of that?
What are you talking? Okay, you're saying just an open box and
Yeah, it's like just imagine a shut box that could contain a vacuum.
Okay, no.
Now
Yeah, was it an open box or a shut box?
I'm getting to the open box, but so that you can understand what I'm talking about, I'm going to build up.
Okay,
Closed box of
closed.
vacuum.
Okay, vacuum chamber. Can we just call it that?
Sure.
Okay.
Vacuum chamber. Cut a hole in the bottom. The air goes in. I stick my hand through the hole, and when we glue the place so it's sealed down.
Mm-hmm.
Then we cut the top off. Now it's just a box around my hand with no top.
Okay, the first thing that happened was all of that vacuum immediately equalized.
I
Now
agree.
there's no more vacuum.
I agree. Totally fine. That's where I was trying to get anyway. I'm just trying to get you to understand the image.
Nature abhors a vacuum.
Yeah, that's fine. Okay,
You know
so my hand's in there.
Into them. Okay.
So my hand's in there, and there's no top anymore. We cut that off.
Mm-hmm.
No containment by the box, yet my hand is still feeling air pressure because there's air in the box, and whatever is causing the air pressure is still happening. Where is the containment?
What are you? You're simply saying the air that we breathe right now requires containment, but where is it?
No, well, I'm not saying it requires containment. You said there's no gas pressure. Like you said, A, arrow B. If there's gas pressure, then there's containment.
That's true.
Right? Yeah. So if there's gas pressure, there's containment. Now, if I can show you no containment, then you should say, oh, there must not be any gas pressure in that situation.
You don't have the ability to show no containment.
Okay, well, is gas contained by an open top box?
No.
Okay, so there's no containment in my open top box.
But now we're just defaulting back to basic air, which is all around us.
That's right. That's fine. We're basic air. I don't know. Maybe you were confused about that. You thinking I was trying to do something else. I'm just talking about basic air.
Yes, okay.
And there's no containment that I see from the box because the box is open on the top. No containment should mean no gas pressure, no air pressure, but obviously there is air pressure. So where's the containment coming from if this initial claim that gas equals air pressure equals containment is true? Then there has to be containment still in this example because there's still pressure. You see what I mean?
I just don't see why any of that demonstration is necessary when all you have to do is say, we have air pressure. Where's the containment?
That's fine. It's necessary. It's not necessary. But in the example, where is the containment? Because there is still gas pressure.
Why is the box around your hand necessary for any of this? You're simply saying,
just to visualize, just as a visual aid to emphasize that the box is obviously not offering containment because it's open. So where's the containment coming from?
All right. Why are you putting this on me?
Well, you said
if
there's gas pressure, then there has to be containment.
That's correct.
Gas pressure, there has to be containment.
Containment.
We agree that there's gas pressure on my hand in the box.
Mm-hmm.
So there has to be containment according to the thing that you said.
I agree.
So where's the containment?
It's somewhere. I mean, I can't go point to what is containment.
What containment is causing this gas pressure on
I
my
just-
hand.
Okay. So what you're going to hear in the chat over and over again is what they call the firmament. Now,
Okay.
I can't travel to the firmament, so I can't go show it to you.
Okay.
But what I can say is,
But is that your answer? That the firmament is the one giving the containment?
well, you can call it the firmament if you like. That's what the
Okay.
Bible calls it.
Okay.
But what I do know is that all gas pressure requires containment.
Right. That's what you said.
I,
So
you know,
so there is some containment. So there must be a container or a containing force or something.
certainly.
Okay.
However, I'm not going to describe it. I'm not going to be
Okay.
able to tell you what shape it is. I'm not going to be able to tell you how far away it is. All I can tell you is I'm definitely sure that there is containment because we have gas pressure.
But how did you come to believe that this is true when I can show you an open box that obviously isn't providing containment and there's still gas pressure? Where did you get this idea that gas pressure would require containment? Because it seems like I'm showing you there's no containment, there's still gas pressure, but you must then say, if you're going to defend this idea, that there is containment from something else. But that's just begging the question, like, how do you know there's containment for something else? Because I cannot see gas pressure without containment. Well, how do you know that? It seems like you're seeing it right now. But so you know what I'm saying?
I think you're working it out in your head right now, where we're at an impasse. Okay.
Mhm.
There's no need for any open box around your hand here.
Correct.
All you're saying is, well, I don't see a container.
Correct.
I know you don't. I know you don't.
Yeah.
I don't see it either. It's really kind of a. I see where you're. Why can't I see this container? And I feel the need to see the container, and I kind of sympathize. And yet we have the gas law. PV equals nRT. Always true. It is a law. It is not.
I don't care about any of these scientific laws or bullshit. I just want to know the facts and the logic. What some combination of letters. Who gives a shit about that? How could we say that it's always true? If we accept that it's always true, sure, then whatever. If you accept that, that's tautological at that point. If you accept that there always has to be a container and whatever volume and whatever that equals this and that, but I don't care about any of that. I'm starting from first principles. How do I know that this law is true, that we need containment?
Okay, so
that we need volume, or that we need contained volume, or whatever.
So regardless of whether or not you like the fact that I use letters to describe things that we know are real, pressure, volume, temperature, they are always observed to be true in all controlled environments where we put those three things in tension: pressure, temperature, and volume. They behave in ways that are always predictable when observed.
If you establish a container, then those things that equation works.
That's correct.
But okay, so if there's a container, then the law works. If there's a container, then the law works. The law working doesn't mean there's a container.
I didn't say that it did. I said,
where are we getting the idea that seemingly without a container, I'm feeling air pressure? How do you know there's a container?
What do you mean seemingly without a container? Where does it seem that there's no container?
Like there could be a container or there could not be a container. I don't know which one there is. What would make you think there's a container?
Because we have gas pressure.
That's based on the law. So if the law is right, then that's affirming the consequent.
Go back to your previous conditional statement that you wrote on your little piece of paper. GP, if GP, then container.
Right.
Okay.
Right. But why would we believe that this if then statement is true? You said because it's the law. Okay, so let's say the law works.
No, we're done. Come on. All right.
What'd you say?
It is first. It is always observed in all environments when there is gas pressure, there is containment. Okay.
Well, I don't. What do you mean? Because I don't see a container. I'm not observing that right now. I'm feeling gas pressure. We've already agreed on that. I'm not observing a container, so it's not in all.
We observe the behavior of gas. It
Right.
is well defined in all environments where you can study the behavior of the gas. And
Okay.
in order to create the pressure, you have to have containment. Always, when you have a vacuum, the vacuum always equalizes the pressure. Gas fills all available space, always. That is a law. So if we have arbitrarily large amounts of space, then the gas pressure, the gas we have here, will simply fill that space, which in the heliocentric model is, and this is the last time I'm going to say this, okay? In the heliocentric model, that space is effectively infinite, and therefore we would have no atmosphere. Gas pressure cannot exist immediately adjacent to a vacuum without containment, period. That is a law.
Wait, hold on. So you're skipping some steps, I believe. If you have a bottle of gas in a larger vacuum, then you unseal the bottle of gas.
Mm-hmm.
There is still air pressure for some time.
How long?
Inside. Well, it depends on how big the bottle is, of course. Right?
It's essentially instantaneous. The air rushes out with great speed into any vacuum.
Well, that's fine. I agree with that. That's fine. If you have a normal pressure inside a vacuum, then the air will rush out. But if you had a huge amount of air, it would take some time. It wouldn't be instantaneous. It would be minutes, hours, right? I mean, just like a balloon that's pressurized compared to the normal pressure of the air, it doesn't deflate instantly. It deflates over time, and the bigger the balloon, the more time it takes, right?
Yeah, sure. Okay. I mean, we're talking about the heliocentric model here, though. We're talking about 10.
I agree. We're just using examples to build up fundamental principles so that we can evaluate the model, the bigger model. So now imagine for a moment that we had a balloon that we unsealed and it's leaking out air, and we can make the hole very small, we can make it very big, whatever. It'll change how fast it leaks, of course. Imagine we were pumping air into the balloon at the same time. Now, if we are creating more gas, which trees do, and which the internals of the earth do, then the air could leak out forever, potentially, and we could always still have more.
I mean,
until the earth runs out of stuff.
We can fantasize all we want about this system that you're creating, but
do you think that the globe model has air leaking out to space?
What are you talking? Leaking out
in the globe model? If you talk to McToon or something,
no.
Would they say that air leaks out into space?
No, they would never say that.
I believe that you're wrong about that. I asked Gemini before our conversation. I mean, they might not be smart enough to know, but I asked Gemini before our conversation, and they said every day, 20 Goodyear blimps full of helium and stuff leak out into space.
I think they would probably say escape out into space, because
sure.
Leak out into space would indicate that there was some solid container that had a little pinprick in it, and it was leaking out like it was a balloon.
Gets pushed out or whatever they would say.
First of all, I don't have any interest in sitting here and reifying the heliocentric model. And
we have to if you want to examine the heliocentric model,
we've already
a steel-manned version. I mean, you said the model does not believe that air is going out into space, but actually it does. So we have to if we're going to attack the heliocentric model, honestly, we have to use the best version of it.
Okay, there is no version of it that doesn't rely on gravity. Okay,
that's fine. But that's not what I'm talking about right now. You're often changing topics. What I'm talking about right now is that you thought the heliocentric model says that nothing effectively is getting out into space of our atmosphere. And that's wrong. The heliocentric model, according to Gemini AI, says that 20 Goodyear blimps every day full of helium, and mostly helium, I think it was, hydrogen maybe, leak out. And I said, well, how does it get replaced, Gemini? And they said, oh, well, there's radioactive decay in the center of the Earth, and that causes hydrogen atoms, which is just basically a free proton or something that it picks up a couple of electrons, picks up hydrogen. And they said the helium, the sun's rays come in, and what was it, like methane or something gets broken up by the sun's rays, and it produces more helium. And I said, well, then how does that thing that's getting broken up get replenished? And it was, through some process of biological synthesis or whatever it is. So anyway, all I'm saying is, on one aspect of the heliocentric model, you didn't understand what the heliocentric model was, and it actually agrees with you. So the critique that, oh, well, air would be leaking out, I mean, it is leaking out. It is leaking out. And so to say that, oh, if air is leaking out, then the heliocentric model is wrong, that's not true. It is compatible with air leaking out. It is known that air leaks out by some people. I assumed that it was, I had to ask Gemini, I didn't know. This was a good argument to me with the first time I heard it from a flat earther. I was like, oh yeah, vacuum, why wouldn't air leak out? But it does leak out. And it gets regenerated too. And then we could talk about, well, why doesn't it all leak out instantly? And that's where we have to have a fundamental understanding of gravity being related to mass or even density. Even density. Like you said, denser things stay down. So even with your own model of how things propagate vertically, whatever you want to call it, your idea of things, your observations or whatever, you think that denser things stay lower than less dense things. So you really shouldn't have a problem with the vacuum of space staying higher and the air staying lower.
What part of a vacuum cannot coexist next to gas pressure without instantaneous equalization?
Yes, you're saying that this is true, but I've pointed out that I don't know how you've gotten to here. I know how you've gotten here. Good. You looked at all examples of containment following the law. Then you said, oh, so if the law is true, then there's always containment. That's the flaw that we started with today. And then further, even if those problems didn't exist, that fallacious reasoning didn't exist, it's contradicting your other thing about density. Your thing about density is that dense things should stay lower. So even if you have all this law, gas pressure, whatever, that's in contradiction with your other belief.
What's the contradiction?
You believe that air, which is more dense than the vacuum, should go up because you see it in some whatever, blah, 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 experiments and whatever. What?
What vacuum?
Space. You believe that air should go up if there is a vacuum.
You made up space.
Right. You believe that if there is this made-up space vacuum, the air should go up. Therefore, since we don't see the air going up, which we do to some extent, but if we don't see the air going up, then the made-up space vacuum is false. I'm not saying that there is a space vacuum. I'm assessing your logic.
No,
your argument.
You're not.
I am. You said, hey, Globers, if there's this vacuum, then the air should escape. If there's the vacuum, the air should escape. We don't see the air escaping, therefore there's no vacuum. That's one thing you're saying. But why would you expect escape when the air is more dense than the vacuum? You'd expect it to fall. If you believe that dense things go down. So there's a contradiction there.
No, there's not.
Okay, I mean, you could say there's not, but I mean, I would prefer an explanation how there's not.
Well, I'm going to give you an explanation, okay?
Sure.
Which I have done 3 times already. And all you do is just find a way to go back to saying this exact same thing again. It's very simple. A prerequisite for gas pressure is containment. Within that system.
You're telling me this again.
Okay,
you're telling me this again.
You understand?
And even if I believe all that's true, it seems to be in conflict.
I have let you grandstand nonstop, and I have been very polite, and you have been interrupting every single time I speak. Okay?
I don't think that's a fair characterization, but go ahead and speak.
Go back and watch the video then.
Go ahead and speak.
It is a prerequisite for to have gas pressure that there is containment. Within that system, you observe that there is a density gradient. I don't have to sit here and pretend with you that there is a vacuum directly adjacent to gas pressure. And I know that you want to say, okay, well, You just assume that gas pressure requires containment. But how do you know? Well, because in all instances, you observe gas always behaving this way. And you're saying, well, how do you know? You don't see the container. Okay, without containment, there is no gas pressure. That's one of the only things that science really ever provided us with that is fully reliable all the time. All right? And I am not going
let's say that's all true. Let's say that's all true. Let's accept that as all true.
It's all true.
Let's accept it as true. So you're saying that dense things only fall because there's a container?
No.
Like if there was no container, then the density thing would be gone?
No. Now, are you deliberately misunderstanding me? It is a very simple case of there is
dense things go down
within a system that has containment.
Right. So
dense things going down, that's one observed law of our world. And one thing we can actually show repeatedly, you're gonna write another if-then statement for me.
No.
And then one thing you can show over and over again with no exceptions is that when a vacuum is next to gas pressure, it immediately equalizes. And in the case of the heliocentric model, you have infinite vacuum. Therefore, it would be infinite equalization. There would be we would live in a 10 to the minus 17 torr vacuum and we'd all be dead. It is as simple as that. Therefore, there is containment.
So if dense things fall down, that means there's a container?
Nope.
Or dense things can fall down without a container also.
Okay, now you're glitching out on me.
I'm just asking you what's your opinion. Is it true that if there's no container, dense things could still fall down, or do dense things fall down because there is a container?
Gas pressure is available because there is a container.
Okay,
things falling down is a separate thing.
Well, I don't think that things falling down is a separate thing from whether the air should fall down.
Well, then you should have listened better.
I mean, obviously that's not true. Whether things fall down and what causes that is intimately related to whether we would, what we would expect to see, in a flat Earth model, in a globe model with air pressure, and whether air goes up or down. Anytime I bring up something like solids or whatever, you always try to say, well, that's very different.
It is obviously different. Everybody knows that solids and liquids.
Everything is different than everything else. This pencil, if I clone it, it's still different because it's in a different spatial location. There's differences between everything. If every argument you're going to just say, well, that's different. I mean, well, yeah, you're always going to be right. It's always different, but there's fundamental similarity, like between horizontal movement and vertical movement. Yeah, they're different, but they're probably related, probably the same kind of thing, but you could always say, nope, it's different. It's different. You could always say that. And it wouldn't be wrong. There's always differences between everything.
You still need to show me gas pressure without containment.
Here you go. There it is. Here it is. Where's the container? How do you know? Oh, well, I know there's a container because when I've seen us create a container, then we have gas pressure. And there's gas pressure here, so there must be a container.
Yeah, nailed it.
That's affirming the consequent.
No, it's not.
That's literally what I just said. How do you know there's a container here? I know there's a container here pull up
the if-then statement that began.
Yeah.
Pull it up.
Every time we create a container.
Hold the GP. No, you said GP, then C. If GP, then C. Show me. Put that back on the screen.
GP, then C. C, then GP.
Which one am I affirming?
So what you're saying?
Which one am I affirming?
I don't use that language, so it's hard for me to. I don't use that language.
Okay, well then maybe you need to learn. Okay.
No, I just have a different name for it.
Affirming the consequent means you affirm the then. If A, then B. Affirming B is affirming the consequent.
Affirming meaning what? Affirming meaning what?
Shut up. If A, then B, okay?
Yeah.
If gas pressure, then containment. I affirmed gas pressure. That's the antecedent. I affirmed the antecedent, A. It's not affirming the consequent. You need to learn your fallacies.
Okay, big words, that doesn't mean anything to me. We just have simple letters and arrows. I'm not impressed by big words. If there's gas pressure, then there's
You
containment.
just said I was affirming the consequent. That's what
Right.
you
I'm just
said.
trying to use your language to say that you're saying that
I
if
get
B,
it.
then
You're
A.
trying to use words that you don't know the meaning of.
Well, okay, maybe that's fine. That's fine. So I'll just say what I'm trying to say. You said, show me gas pressure without containment. I said, here we go. Here we are with gas pressure. Where's the container? I don't see a container. It seems like there's no container. You said, no. There has to be a container in this example, in the real world, and it's just wherever there's gas pressure. How do you know? Well, whenever we create a container, then we establish gas pressure. Like, unless we pump out all the gas. Like in every situation where we create a container, there's gas pressure, and there's gas pressure here, so there must be a container.
You just wrote that down.
So how do you know there's a container here?
Whoa.
Because
you just wrote down C, if C, then
Yeah.
GP. If container, then gas pressure. That's a silly thing to
no,
write
that's
down.
not the English translation of what I wrote down. That's not what I'm trying to represent.
There it is, right in front of me. If
Yeah, but that's
C,
not
then
English. That's not
GP.
English. That's just letters. What I mean by these letters is
calculus.
every time we create a container to establish gas pressure, we do establish gas pressure.
I don't even know why that's part of the conversation. I didn't say anything like that.
Okay, so how do you know there's a container? You said you can't show an example where there's gas pressure without containment.
Yeah,
Showing you an example with gas pressure where I think there might be no containment. How do you know there's a container on the atmosphere?
You only think there might be no containment because you think you live on a ball in a vacuum.
How do you know there's containment?
Because there's gas pressure. I don't know how many times I have to tell you.
Okay. Why would gas pressure mean there's containment?
What? I've already told you too many times. I don't have to repeat it again.
Okay. So if you look into this logic right here, this logic that we're going over multiple times, I think you will find it's part of the answer to what I think is the confusion about this vacuum argument for flat Earth, which was totally reasonable to me. At first, when I heard this vacuum argument, I was, why would there be a vacuum next to us and yet we still have air? That's weird. And then I looked into it and thought about it and followed the logic, and I realized, oh, wait a second. This is not as clear of a good argument as I thought, because like we just saw, I show you an example of gas pressure, perhaps without containment. You say, no, there's definitely a container. How do you know? Because there's gas pressure. If there's gas pressure, GP, then C, there must be a container. Well, how do we know that this if-then statement is true? Well, because we've seen when we build experiments with containers, to produce gas pressure, we have gas pressure, which is B arrow A. How do you know A arrow B is true? Well, B arrow A. Well, okay, but that's affirming the consequence or whatever you want to call it. It's the flaw we started with.
Scientific law is true because it's always observed to be true.
But it's not. But it's not.
Okay,
I'm observing it right now. It doesn't seem like it's true.
It's always observed to be true, except this one time when you say, by the way, I have space. Space. You might as well be doing that right now. Space. That's how I know. This is the exception. It's also known as the special pleading fallacy.
Right, but that's fine. But it aligns with your density thing. It would make sense if you're right that denser things are lower. It would make sense that there is no container. It's just denser than nothing, and so it stays lower than nothing.
We can talk about dense things going down, or we can talk about gas pressure requiring containment. We're not going to talk about both because you're just.
But we can't talk about both because that would defeat the argument that you're trying to make.
No, because you're just going to very.
We know that gas is a thing. If you already established that gas follows this law too, denser gas falls within other gas. You've already established this stuff.
I have been very patient here. You interrupt every time. It has just gotten so tedious. I've already answered your question probably a dozen times by now.
I do not disagree. You've responded, and we're repeating ourselves. That's true. I'm just trying to make some headway because we are both repeating ourselves. That's fine.
We had a hard stop. We had a hard
Yeah,
stop.
you can go. That's fine. It's fine. We're
All right.
repeating ourselves. That's fine. It
Bye,
was good
everybody.
talking to you.